Hello! Today, we're going on a fun adventure into the world of matrices. Think of a matrix as a super organized box of numbers. It's a way to keep numbers in neat, rectangular rows and columns. We use these boxes for all sorts of cool things, especially in business. You'll be surprised to learn what we can do with these special number boxes. In this video, we're going to learn about matrices and the math we can do with them. By the end, you'll be able to solve problems using these amazing boxes of numbers. First, let's talk about where we see these matrices in the real world, especially in business. You might not realize it, but matrices are powerful tools for making smart business decisions. Imagine a shop selling different types of shirts in different colors. A matrix is a perfect way to keep track of the inventory. Let's say they sell small, medium, and large shirts, and they come in blue, red, and green. We can build a matrix, a grid, with sizes as rows and colors as columns. Each number inside tells you exactly how many of that specific shirt they have in stock. This makes checking inventory super easy and fast. Matrices can also help businesses manage their money. They can be used to track expenses over time or to forecast future sales for different products. By arranging all these financial numbers in a matrix, businesses can analyze them more efficiently and spot trends to make better financial plans. And the really cool part is, we can use matrix math to do things like calculate total sales for all shirts, or project how much money the business will make next month. So, matrices are like a secret superpower for making businesses successful. Now that we know how useful matrices are, let's look inside our box of numbers. Matrices come in different shapes and sizes. Just like a toy box can hold small cars or large blocks, there are different types of matrices. A matrix's size is described by its order. We say a matrix is M by N, where M is the number of rows and N is the number of columns. For example, a matrix with 3 rows and 2 columns is a 3 by 2 matrix. First up, we have a row matrix. As the name suggests, a row matrix has only one row. It's like a single line of numbers. For instance, a 1 by 3 matrix. And its partner is the column matrix. A column matrix has only one column. It's like a tower of numbers. A 3 by 1 matrix is a column matrix. Next is a very special type called a square matrix. A square matrix is special because it has the same number of rows and columns. A 2 by 2 matrix is a square matrix. A 3 by 3 matrix is also a square matrix. Its shape is a perfect square. There are other interesting square matrices too. A diagonal matrix is a square matrix where all the numbers are 0, except for the numbers along the main diagonal. An identity matrix, often called I, is a special diagonal matrix where all the diagonal numbers are 1. The zero matrix, or O, is a matrix where every single number is 0. All of these have special properties we'll learn about. So, just like shapes in a puzzle, matrices have different types. We've seen row, column, and square matrices. Okay, let's play a game called Find the Twins. Today, our goal is to understand what it means for two matrices to be equal. It's simpler than you might think. For two matrices to be twins, or equal, they need two things. First, they must have the exact same shape, or order. Second, every single number inside one box must match the number in the same spot in the other box. Let's look at an example. Here we have two matrices. Are they equal? Let's check. Do they have the same order? Yes, they are both 2 by 2 matrices. Does every number in the same position match? Let's see. 1 equals 1, 2 equals 2, 3 equals 3, and 4 equals 4. Yes. So these two matrices are equal. Now, let's try another one. That's a bit of a trick. What about these two? Are they equal? Let's check the first rule, same order. Matrix C is 2 by 2, and matrix D is 3 by 2. Uh-oh, they have different orders. Since their shapes are different, we don't even need to check the numbers. They are not equal. So, remember, two conditions. If either one is not met, the matrices are not equal. Now you know how to tell if two matrices are twins. Fantastic! Now for the fun part, doing math with our matrices. First up, the easiest operation, scalar multiplication. Our goal here is to learn how to multiply a whole matrix by a single ordinary number. Think of it like scaling something up or down. A scalar is just a fancy word for a single number. So, multiplying a matrix by a scalar means multiplying every single number inside the matrix by that scalar. You take one number and use it to scale the entire box of numbers. It's like changing the volume on your music. Every sound gets louder. Let's work through an example. Imagine we have this 2x3 matrix. Let's call it A. Now, let's say we want to find 4 times matrix A. This is written as 4A. The rule says we multiply every number in A by 4. So, we take 4 and multiply it by 1, then by 2, then by 3, and so on for every number in the box. After doing all the multiplications, we get our new matrix. And here is our final answer, the matrix 4A. It's a brand new matrix where every number is 4 times as big as it was in the original matrix A. Notice the order of the matrix didn't change at all. Let's recap. To multiply a matrix by a single number, you multiply every single number inside the matrix by that scalar. You've mastered scalar multiplication. Ready for some matrix mixing? We're going to learn about matrix addition and subtraction. Think of it like mixing 2 different batches of cupcakes. We need to know how to combine the numbers inside our boxes. There's one golden rule for adding or subtracting matrices, and it's a very important one. The matrices must have the exact same order or shape. You can't add a 2x3 matrix to a 3x3 matrix, just like you can't add apples and oranges. If they have the same order, the process is super easy. Let's start with addition. To add 2 matrices, you simply add the numbers in the same positions. It's called adding corresponding elements. Let's see this in action. Here are 2 matrices, A and B. First, check the rule. Are they the same order? Yes, both are 2 by 2, so we can add them. We add the top left number of A to the top left number of B. That's 1 plus 5, which gives us 6. We do this for every single position. 2 plus 6 is 8, 3 plus 7 is 10, and 4 plus 8 is 12. And just like that, we have our answer, A plus B. Subtraction works the exact same way. Let's do an example. Let's use the same matrices A and B and find A minus B. The order is still the same, so we're good to go. Now we subtract the numbers in the same positions. Be careful with your signs. 1 minus 5 is negative 4. 2 minus sec is also negative 4. 3 minus 7 is negative 4. Our answer for A minus B is the matrix with all negative 4s. So, to recap matrix addition and subtraction. First, always check the order. They must be the same. Second, just add or subtract the numbers in the same spot. That's all there is to it. This next operation is a bit more complex, but it's incredibly powerful. Matrix multiplication. Don't worry, we'll break it down step by step. Our goal is to learn how to multiply 2 matrices together. Unlike addition, there's a different rule for order. It's the most important thing to remember. The number of columns in the first matrix must match the number of rows in the second matrix. It's like a bridge connecting them. If the numbers don't match, you can't multiply them. If they do match, you can. Let's use an example to see how to do it. Let's multiply a 2 by 2 matrix A by a 2 by 1 matrix B. First, check the rule. A is 2 by 2, B is 2 by 1. The inner numbers are 2 and 2. They match, so we can do it. The answer, AB, will be a 2 by 1 matrix. To find the first number in our answer matrix, we take the first row of A and the first column of B. We multiply the first numbers and add them to the product of the second numbers. So, it's 1 times 5 plus 2 times 6. That's 5 plus 12, which equals 17. That's our first number. To find the second number, we take the second row of A and the first column of B. We multiply the first numbers, 3 times 5, and add it to the product of the second numbers, 4 times 6. That's 15 plus 24, which equals 39. That's our second number. And there you have it, the final product matrix. Remember the rule, first row times first column, second row times first column, and so on. Now you're multiplying matrices. There's a special move matrices can do. It's called finding the transpose. Think of it like taking our box of numbers and flipping it, or rotating it. Our goal is to learn how to transpose a matrix. The rule for transposing a matrix is very simple and elegant. You just swap the rows and the columns. The first row becomes the first column, the second row becomes the second column, and so on. It's a neat little flip. Let's work through an example. Here's a 2 by 3 matrix A. Its transpose, which we write as A with a little t, will have its rows and columns swapped. So, A transpose will be a 3 by 2 matrix. The first row of A, which is 1, 2, 3, becomes the first column of A transpose. The second row of A, which is 4, 5, 6, becomes the second column of A transpose. It's that easy. The whole matrix just got flipped. Now, here's a fun fact about square matrices. If you transpose a square matrix, something interesting happens. Let's look at this 2 by 2 matrix B. When we transpose it, the first row becomes the first column, and the second row, 3, becomes the second column. Notice that the numbers 1 and 4 on the main diagonal didn't move. Only the numbers off the diagonal, 2 and 3, swapped places. So, to recap the transpose, just swap the rows and the columns. It's like flipping the entire box of numbers. You've got the flip down. Let's dive into some detective work. Our goal is to find the fingerprint of a square matrix. This fingerprint is called the determinant. The determinant is a special single number that only square matrices have. It tells us a lot about the matrix, like whether it can be inverted. Let's start with the simplest case, a 2 by 2 matrix. For a matrix with numbers A, B, C, and D, the determinant is calculated using a specific formula. You multiply the numbers on the main diagonal, A and D, and then subtract the product of the numbers on the other diagonal, B and C. Let's see this with real numbers. Let's find the determinant of this matrix. We use the formula 2 times 7 minus 3 times 5. That's 14 minus 15, which gives us -1. The determinant of this matrix is -1. It's that easy for a 2 by 2 matrix. Now, for a larger matrix, a 3 by 3, it's a bit more involved. The formula is longer, and we use a concept called expansion by cofactors. But don't worry, the core idea is the same. The determinant of a 3x3 matrix is a bit more complex, but the idea is to break it down into calculating 2x2 determinants. The important takeaway here is that a determinant is a single special number that comes from a square matrix. To understand the 3 by 3 determinant, we need two new tools, minors and cofactors. Our goal is to learn how to find these building blocks for larger matrix calculations. They might sound complicated, but they're just steps in a process. Let's start with a minor. For any element in a square matrix, its minor is the determinant of the smaller matrix you get by removing that element's row and column. Let's use a 3 by 3 matrix as our example. Let's find the minor of the number 1. We go to the matrix, highlight the number 1, and then cross out its row and its column. What's left is a smaller 2 by 2 matrix. 5, 6, 8, 9. The minor of 1 is the determinant of this 2 by 2 matrix. So it's 5 times 9 minus 6 times 8, which is 45 minus 48, or -3. Next, let's find a cofactor. A cofactor is closely related to a minor. The cofactor is the minor multiplied by either 1 or -1, depending on where the element is in the matrix. It's like applying a checkerboard pattern of signs. Let's find the cofactor of 1, which is C11. The cofactor is -1 raised to the power of 1 plus 1, times the minor we just found. That's -1 squared times -3. -1 squared is +1. So, the cofactor C11 is +1 times -3. In this case, the cofactor and the minor were the same. Let's try one more. Find the cofactor of 2, which is C12. First, we find its minor, M12. We cross out the row and column of 2. The remaining matrix is 4, 6, 7, 9. The determinant is 4 times 9 minus 6 times 7, which is 36 minus 42, or -6. Now, we use the cofactor formula. The sign for the second element in the first row is negative. So, C12 equals -1 times -6, which is +6. To recap, minors and cofactors are steps in a bigger process. A minor is a smaller determinant, and a cofactor is just the minor with a possible sign change. Great job! These are tricky, but you're getting them. Now we have all the pieces to find the 3 by 3 determinant. Let's combine what we've learned. Our objective is to use minors and cofactors to correctly calculate the determinant of a 3 by 3 matrix. To find the determinant of a 3 by 3 matrix, you pick any row or any column. Then, for each element in that row or column, you multiply the element by its cofactor and add them all together. This is called expanding by cofactors. Let's write out the formula for expanding along the first row. It's A111 times its cofactor C111 plus A12 times its cofactor C12 plus A13 times its cofactor C13. Let's use our example matrix. Let's find the determinant of this matrix by expanding along the first row. We already found the first two cofactors. Remember that C111 was -3 and C12 was 6. We just need C13, the cofactor of 3. The minor of 3 is the determinant of the 2x2 matrix that's left after we cross out its row and column. That's 4 times 8 minus 5 times 7, which is 32 minus 35, or -3. The sign for C13 is positive, so C13 is also -3. Now we have everything we need. Let's plug the numbers into our formula. The determinant of A is 1 times -3 plus 2 times 6 plus 3 times -3. That gives us -3 plus 12 minus 9, and -3 plus 12 is 9, and 9 minus 9 is 0. So, the determinant of this matrix is 0. Let's review. To find a 3 by 3 determinant, pick any row or column, multiply each element in it by its cofactor, and add the results. That's how you find the 3 by 3 determinant. We're building towards a very important tool. Our next step is to find something called the adjoint matrix. Don't be scared by the name. It's just a special matrix we create using the cofactors we just learned about. Our goal is to learn how to find the adjoint of a matrix. The process has two main steps. Step 1 is to find the matrix of all the cofactors. You just replace each number in the original matrix with its own cofactor. Step 2 is to take the transpose of that cofactor matrix. This final transposed matrix is called the adjoint. Let's use a simpler 2 by 2 matrix to make it clearer. Here's our 2 by 2 matrix A. Let's find its adjoint. First, step 1, find the cofactor of each element. We'll need the checkerboard sign pattern for a 2x2 matrix. Let's list them out. C11 is the minor of 2 with a positive sign. The minor of 2 is the determinant of the remaining matrix, which is just 7. So C11 is the minor of 3 with a negative sign. The minor is 5, so C12 is -5. C21 is the minor of 5 with a negative sign. The minor is 3, so C21 is -3. And C22 is the minor of 7 with a positive sign. The minor is 2, so C22 is 2. Now we build our cofactor matrix, C. We arrange these cofactors in their corresponding positions to form the cofactor matrix C. Step 2. Find the adjoint. This is the transpose of our cofactor matrix. To get the adjoint of A, we take our cofactor matrix C and swap its rows and columns. The first row becomes the first column, and the second row becomes the second column. And there it is, the adjoint matrix of A. So, to recap, find all the cofactors, arrange them into a new matrix, and then take the transpose. That's how you find the adjoint matrix. You're doing great. Okay, the grand finale. We're putting everything together to find the inverse of a matrix. The inverse of a matrix, written as A, is like the number 1A. It's a special matrix that when you multiply it by the original matrix A, gives you the identity matrix, I. The inverse is incredibly useful. It allows us to divide matrices, and it's the key to solving systems of linear equations. There's one crucial detail before we begin. A matrix can only have an inverse if it's a square matrix and if its determinant is not 0. If the determinant is 0, it means the matrix is singular and has no inverse. This is why finding the determinant was so important. If it meets those two conditions, here's the formula to find the inverse. The inverse of A is equal to 1 over the determinant of A multiplied by the adjoint matrix of A. This formula connects everything we've learned. Let's use our 2 by 2 example. One last time. Here's the matrix we've been working with. We already know two things about it. First, we found its determinant to be -1, which is not 0, so we know an inverse exists. Second, we found its adjoint matrix. Now, we just put them into the formula. The inverse of A is 1 over -1, which is just -1. And we multiply that by our adjoint matrix. We perform scalar multiplication, multiplying every element by -1. This gives us our final answer, the inverse of A. To recap, finding the inverse is the grand combination. You first check the determinant. If it's not 0, you find the adjoint. And then you put them into the inverse formula. You've now unlocked the power of matrices. Wow, what an adventure we've had today in the world of matrices. Let's quickly recap what we've accomplished. First, we learned that matrices are powerful tools for organizing and analyzing data, especially in business applications like inventory and finance. We learned that matrices come in different types, like row, column, and square matrices. We also learned how to perform basic operations, adding, subtracting, and scalar multiplying matrices. We then dove into more complex but incredibly useful operations, matrix multiplication, transposing a matrix, finding its determinant, and using cofactors to find the adjoint, all to finally unlock the inverse. You now have a solid understanding of the fundamental concepts of matrices. These boxes of numbers are the building blocks for so much of mathematics, science, and technology. You've done an amazing job today. Keep exploring, and I'll see you next time.